You remember that ionic bonding involves the transfer of electrons, a difference in electronegativity that is so great between the metal and nonmetal that the metal gives up the electron, the nonmetal takes it, and in that way, both complete their valence shell. Most obviously, it is the case for the nonmetal that gets the electron, but it's also the case for the metal, which, relinquishing the electron, ends up having a full valence shell just at the n-1 energy level. We don't usually use electron dot diagrams to represent these ionic compounds, but here I've just sort of shown you the thing that you've seen 2 or 3 times before. The idea that sodium having that 1 valence electron and chlorine having this 7 valence electron shown in black ends up, as they come together, the electron affinity of chlorine and the ionization energy of sodium in conjunction perhaps with some energy in the local environment produces then this electron transfer. We then end up with 2 ions, right? An ion is a atom that has a charge because of loss or gain of electrons. Sodium has a positive charge. Metals lose electrons. I'll say that probably a dozen times. And Cl has a minus charge. Both of these are 1 in terms of their unit, +1 and -1. And because of those charges, opposite charges attracting, the ions come together and form a crystalline structure because of those strong electrostatic forces. Then ionic bonds are themselves essentially a community thing because all of these ions are packed together in this nice, neat crystalline solid where we end up with the attraction between neighboring ions with different charges. The important thing to note here, though, and this causes students a lot of trouble, is that the formula that we write for an ionic compound is not the same as the formula we write for a molecular or covalent compound. In the case of the covalent compound, the formula actually is the molecule, a discrete unit. In the case of an ionic compound, the formula is a simple empirical one, meaning it just specifies the smallest whole number ratios between cation and anion in order that the formula have electrical neutrality. Let's think about that. We write NaCl, not NaCl2, not Na2Cl, not anything else, because the sodium ion has a +1 charge, the chloride ion has a -1 charge, and as a result, the simplest whole number ratio to give us neutrality is 1:1, and we don't write the ones, so we just end up with NaCl specifying the formula for the ionic compound. Sometimes we call it a formula unit, but it is not the same as a molecule. We do not have 1 sodium next to 1 chloride. What we have are many ions packed together in a regular repeating arrangement of cation and anion to make up the crystal lattice, we actually call it, of the ionic compounds. The strength of these ionic compounds is derived from the total electrostatic attraction that is manifest. The reason we have to write CaF2 is not because 2 fluorines are covalently bonded to calcium. Metal and nonmetal gives us a big difference in electronegativity and electron transfer and ionic bonding, but rather because calcium, being a group 2 metal, is going to be most stable having lost 2 electrons in order to become isoelectronic with argon. Look at the periodic table. And as a result, fluorine only needs 1 electron per atom, right? Because it's in group 17 and will fill its valence shell with the addition of 1 electron. The fluoride ion has a -1 charge. The calcium ion has a +2 charge. And hence, in order to make a formula unit that is neutral, we end up with a formula of CaF2. Again, fundamentally different than a molecular formula, which actually shows the number of atoms that are hooked together. Here, we're purely specifying a ratio. we may or may not get into the details of this, but as a result of that fundamental difference between the two, we can't specify the strength of a ionic bond in the same way we did with molecular compounds, in that we can never isolate just one cation and one anion, or one cation and two anions, or whatever. We have to take a bulk property approach, and we do so by talking about the lattice energy of ionic compounds, which, although can be defined in a number of different ways, can be thought of as the energy that evolves when 1 mole of ionic compound forms from its gaseous ions. And because all these gaseous ions would have very, very, very high energy, and when they all get together into 1 mole of solid ionic compound, they all have quite low energy. Lattice energies are defined in this way, all going to be negative, exothermic, and of course, because nature favors the low system energy, the formation of these ionic compounds is going to be favored in nature, and there are many, many, many ionic compounds out there. All rocks are essentially ionic in their character, as well a variety of other minerals out there in nature. What's the big deal, you want to know? Well, no other, I guess, distinction has such a remarkable effect on the physical properties of the substances. And it has to do with the nature of the forces holding the substance together. For example, in ionic compounds, we have that lattice energy. We have that enormous electrostatic attractive force between positive and negative particles operating throughout the crystal structure. And because that force is so large, all ionic compounds are solids at room temperature, and they all have high melting points and boiling points. They are all mostly soluble in water, a topic we'll take up in some detail later. And they are conductive of electricity when either they are molten or when they are in that same solution with water. Again, a very important intensive property to be conductive of electricity, and this allows then current to be carried by the ions in solution, and as a result, that conductivity makes sense. In covalent compounds, the forces holding the molecules to each other are relatively weak. Do not confuse this with the covalent bond itself, which is holding the molecule together. I'm talking about what we call the intermolecular forces holding the molecules together to each other. Those tend to be relatively weak, and as a result, almost all of our covalent compounds are liquids or gases at room temperature. And those that are solids have low melting points as a result of those weak forces. Likewise, because most of these covalent compounds are relatively nonpolar, they are insoluble in water, and because they do not contain any charges, they end up being non-conductive. So it is very easy to, in most cases, to identify a substance as being ionic or covalent simply by doing a few simple tests, and you will do this in lab with a variety of substances and end up declaring them to be either ionic or covalent based on their physical properties.